Why is it? A month to go. Okay, so blood. So first of all, we're not memorizing all this, but let's kind of look at this idea because we've kind of done it. When it comes down to the blood, I just sort of want to kind of, in fact, show it here. You're not memorizing that. So the idea of, okay, well, we have water, ions. We kind of see the importance of that. Here's sort of, glucose, etc. But look at some of the proteins. Albumins, okay, fibrinogen, which is going to be involved in blood clotting. We'll talk about that. Globulins, which include the immunoglobulins, right, for our immune system. And that's the idea of these guys being made for the liver. And of course, there's other things as well. And then there is cells, okay? So 3 main types of cells: red blood cells, white blood cells, and these things which we'll see come from megakaryocytes, platelets involved in clotting. Now you look at all these types of white blood cells, we're not being tested on these in class. Next week in lab, we'll start doing a little immune stuff there. So I'm not going to do the immune chapter and kind of deal with it in class because I have other priorities. Again, if you really, really want a lot of immunology, you go, well, it's almost too late, but you go to Dr. Tomford's class because he was an immunologist. Everyone has their little specialty that they do. So he spends several days on it. He's actually retiring in the spring, so you don't have much more chance to see Dr. Tomford. But hey, if you know somebody who likes immunology, I know he's teaching in the spring. I actually end up teaching in the spring. I couldn't do Fridays because of UCSD, but I didn't want to not teach. So it's going to be a weird time. I don't know what's going to do it. So they arrange it like I could do an all day thing, or like we're doing, but from Monday afternoon to Monday evening in Santa Leo, because that was the only time I could actually work and still do the class. So we'll see if people want that, because it goes like, it says 3:30 to 10, but when people, well, I used to teach city college at 10. Haven't you attended classes at night? It really won't go, well, a lot of people did, because I taught city college at night and for years from that kind of time. It really won't go that long because you kind of know how I am with lab. I would probably be out by now or something. But, well, we'll see. Hopefully I can still get people in the class. Yeah, so you guys haven't taken any night classes?
I have.
Yeah.
For stats.
So, yeah, I mean, it's still fun. Okay, well, whatever. No one shows up.
We would have like dinner like in class.
But if you know someone who needs physiology and is willing to do that, versus and kind of wants to be as a teacher.
But here, no one's going to teach it?
What?
Here, no one's going to teach it, or no teachers?
Friday, what's her name? Miranda is going to do an all-day Friday. She has a number for. She teaches, she teaches different ones here. So she's doing that Friday one. Then hopefully I get back. I think UCSD in the fall, if I'm still alive and I'm still teaching here. I think my schedule, because they try to do my schedule because they know I want to do this. It's just they couldn't do it this time. So, because the Friday thing is kind of what I want. So, but I didn't want to not teach, so I tried to do that. We'll see. Okay. Blood cells. So we're not going to deal with all of these right now. And again, I put all this for fun, just to show you how important blood is, why we're not being on. So we're looking at everything, right? I've kind of had this before. You could see idea of the circulation, but what's in the blood being delivered is basically, everything. Now, here's where, and I'm going to put this here for now. Well, actually, I did this. I can erase this now. They kind of show again, when we're looking at these liver proteins. I'm going to get rid of all that. But hematopoiesis, okay? This is, and you may not have heard this term, and right now I have a lot of words here that I'm going to make sort of simple here, but I want to show this picture. So, how many people have heard of stem cells? Okay? Now, there's at least, I teach this somewhere else too, but there's at least, and I'm just going to put this right up here and then do this. Stem cells, basically, their property is they can produce more of themselves, and then they can differentiate, which is to become, right, different cell types. Okay, that's the whole idea of stem cells. I do want to put up here sort of 2 types, and it's kind of important. Pluripotent basically means they can become any cell type. So that potent is like their potency, right? Pluripotent, they basically can differentiate. I just want to use that word, which means they can become all cell types in our body. Okay? Now, the only pluripotent stem cells that we have is, let's go back, way back, when you were a little blastula, like 200 cells. Remember how life was so much easier then? Like, tomorrow, I'm gonna be 400 cells or something like that. But these are called embryonic stem cells. Because obviously, when you started with your 200 cells, they weren't anything, right? They weren't any particular tissue. They weren't nervous system, circulatory system, skin at all. They were these undifferentiated cells waiting to go, and eventually those 200 stem cells became every tissue in your body. Those are the only pluripotent ones that could become basically any tissue. So again, these are found in early embryo. And this again, I'm not going to go out and you could do a lot on stem cells. So these have some controversy associated with them because since they can become any cell type, potentially therapeutically, they can be used. So theoretically, that if you have embryonic stem cells, if we can control them to become, let's say, pancreatic cells, diabetics have lost that, might be able to replace that. Nerve cells, you have damage, and so they have the potential of that if we could control that. One of the issues with it is their source of them are these unused sort of embryos from fertilization clinics. And so it's the idea of, is that, so you have a blastula, right? You do the sperm and egg. So have you created life and are you destroying it to get those stem cells? That's sort of been a controversy over time. The legal things go differently. California allows it, has this sort of thing. And again, you can have your own moral stance and stuff on that. But that is sort of those. That's the only pluripotent ones. We actually have a new kind of cool thing where we could take one of your skin cells and make them pluripotent, but we're not going to talk about that now. But that's the idea of that. Multipotent. Sometimes those are the idea of what we'll call adult stem cells. Which means those cells are in every one of our tissues, okay? And that allows it that as tissue gets damaged or cells die, they can replace them. And so, but they have a different thing. They are multipotent. I guess I put them in the wrong order. They can only become some cell types. Depending on what tissue they're in. If you have skin stem cells, right? Our skin cells are dying all the time, right? They can only become skin cells. They can't become nerve cells or anything else like that. You do have neural stem cells, not many, that can become sort of brain cells, and every tissue has that. But they can only become some cell types. And it says adult, but I mean, again, even there's fetal stem cells. That's another controversy. But every basically you have these are in all your tissues. Okay, so everyone understand the difference between those two, just as stepping back. So again, these potentially could be therapeutic as well, and so it's kind of a cool topic. All right, we get to this now. The reason I get to this is how do we produce red blood cells, white blood cells, and these megakaryocytes which become platelets as fragments? We have a stem cell. And so these are called hematopoietic, if I spelled that right. P-O-I-E.
P-O-I-E.
P-O-I-E. Go ahead.
T-I-C.
Thank you. That's why I don't take off on spelling. Okay. So hematopoietic stem cells, they are basically, as an adult, I think I have, okay, before birth, they're produced in a lot of places besides bone marrow, your liver and your spleen. After birth now, they are in our bone marrow. And they are there to basically, I'll keep this up for a second, to replace all those cell types. And if you look at this, again, we kind of overall on this, red blood cells, as we'll sort of look at, they don't last that long, like 3 or 4 months, okay? White blood cells that you're producing, sometimes hours or days. So we have to keep making these. So you have these hematopoietic stem cells that can become red blood cells, white blood cells, or these megakaryocytes, depending upon what factors go to the bone marrow and tell them what we need. There's all kinds of factors. The only ones I want us to know, this is kind of a cool picture. at least I think. I don't know what I have. I guess I have this. It's just kind of showing sort of this idea of how these stem cells become different cell types. You kind of see red blood cells as they're produced, and they come out here. God, we'll talk about this. They don't even have the purple as the nucleus. They don't even have a nucleus. Wow, they're sort of cool. And the idea, where's the other cool picture? When you talk about platelets, which we all know about, they actually come from these megakaryocytes that have differentiated into them, and they're just little fragments of those. Just kind of a cool picture. So I don't like charts, but I am going to use two of these things. So the idea is, how do these stem cells decide what to become? How do we signal them? And for the white blood cells, there's like a ton of stuff, okay? But these guys are pretty easy, so let's kind of do this. So for red blood cells, it's basically, if we need red blood cells, and we're anemic, etc., who's going to come to help us? What organ? The kidney. Oh, kidney is starting to come into play already. So the kidney produces EPO. Okay, and did they spell that out? Yeah, they spelled that out there. Erythropoietin. And so if we need red blood cells, or if we want to, if we are anemic from chemotherapy, okay, which chemotherapy destroys all of these cells, they're going to give you synthetic EPO, or a kidney produces EPO. Or if you're an athlete and you think, man, I want some red blood cells and I'm going to cheat, you basically can take EPO as well, okay, although we'll start detecting it. So EPO, again, is what I want you to remember, that under those signals, you're going to increase the number of red blood cells, okay, either naturally or synthetically.
What is it a protein?
Protein.
Is it created by the kidney? There are proteins created by the kidney to produce red blood cells?
To send signals to the bone marrow to produce more red blood cells.
Okay.
Are you starting to be amazed by the kidney already? It's not just like a filtering system. It produces hormones. It is a hard worker. So EPO increases red blood cells. We'll get back to that. Lots of factors increase will change white blood cells for the immune response. Yeah, we're not dealing with that in this course because it's too many words, too many things. But how about the idea of clotting factors, okay, which are going to be the megakaryocytes, which become platelets. Actually, I'll put kidney on this. Produce this. Then we have something called thrombopoietin, or TPO. So this is the liver saying, and you can see why, okay, but overall, the liver is going to also be involved in blood clotting, as we're going to see, right? Because basically the liver is helping these stem cells, sending signals to bone marrow to basically have these stem cells now differentiate into basically megakaryocytes. And this is using the compound TPO. That's what I want you to know, for, as far as, and we're going to come back to how red blood cells, having too many of them, might affect something in a bit. Okay? Does everyone sort of get the concept then? There might be one question, just making sure you understand multipotent. In fact, I'll put this over on this too. Mainly produced in the bone marrow, just to have a factoid, versus the early embryo. And just those two components, TPO and EPO. Okay. Hematocrit. Now, we are one of the labs, and I think it's this one, but it's going to be hard to do now. But we want to make sure we understand what hematocrit is, and I mentioned it before, but we're going to do it again. So in blood lab today, usually we got little spots blood, but we got some dog blood. Okay, and so we didn't need your blood to do it, and we would actually do, put it in a capillary tube and actually spit it down and determine the hematocrit and some of the other things. Now I don't know why we don't have any animal blood anymore. So we're going to take, you're going to have a finger prick, and we're going to take a few drops of blood to do some of these other tests. We'll test for hemoglobin. We'll do like a red blood cell count. Put it under the scope because we don't need very much. But unless you guys are good bleeders, we have a good bleeder here. Okay. Oh man. We might do a couple hematocrits. We could fill a little capillary tube and actually do that. But let's just kind of get the idea of what I want here.
During the last.
Any good bleeders? Okay, no. but make sure you control. So hematocrit is, we're gonna spin the blood down in a centrifuge, okay, or if you've done it everywhere else. And that's gonna mean most of the cellular components, there are not many white blood cells. You see that little picture up there? And and we'll actually next week look at a white blood cell count. We'll have these slides that basically, but these are like a blood panel, right? But there's not many of them. So when you spin them down, these dense blood cells, or red blood cells, are going to go to the bottom, and then all the other stuff is going to be at the top. And so the hematocrit, as it says at the bottom there, measures the percentage of red blood cells in your blood. Percentage of RBCs in blood. So let's kind of put these here. And you can see the number is about 50%, give or take a few percent, and it's overall. So we kind of do that. Again, let's say, going from the bottom up to that's 5 centimeters in this capillary tube. If you measure all the way from the bottom to the top of the plasma, 10 centimeters, you can see hematocrit would be 5 over 10, and it's percent times 100 equals about 50%. So most hematocrits, if you look at them, again, we have, like I say, we'll be doing some of this. Most of them, you see at the top, again, in general, females will have a smaller amount based on testosterone, things like that. But it's a pretty big range too. But I'm just saying, it's around 50%. You're not memorizing percentages anyway. So that's what hematocrit actually measures. Do I wait? I might wait. I'm gonna wait on this to apply it to the ZPO. That's hematocrit. That's all you have to know about that right now. Let's look at red blood cells. And again, as I kind of showed last time, a couple of seconds ago, it actually contains no nucleus. And actually all the organelles, even stuff we didn't talk about to make proteins and things like that, it doesn't include any of that. It literally has a specific function. It has hemoglobin, which we'll start to talk about now and then after the respiratory system where we do it, and a bunch of enzymes, basically. There's no mitochondria. And so all their energy has to be through that glycolysis, that fasting, right? Because you don't have mitochondria, you can't do anything else. And there's not gonna be really like factoids like this, like on test, but we kind of want to get us to that. What else about it? Well, we know this. They have a big cytoskeleton that will respond to, he's kind of showing that side, it's got different conditions around it, basically, and overall. And this looked like it was isotonic. What was this in to cause it to swell? Hypo or hyper?
Hypo.
How many people say hypo? Yeah, you're ahead of the game. You just don't even realize it if you take any other class. Okay, and this guy was in hyper, drew the water out, and that's why that was the whole idea of sort of that shape. I'm not putting that on this test. You just had that, right? And most of you did really well on that too. Again, this test, having 13 out of 27 get A's is pretty high percentage, okay? And so, and if you didn't do that well, it's not that as many points overall. So we're gonna deal with hemoglobin. I'm gonna keep this up and erase some things. Right now, again, I'll tell you when we're really getting to something you need to know for this test. But the idea of hemoglobin is it's gonna carry basically the oxygen. And let's see what we need to know. This is a cool picture of the real structure of it. Okay, I was just, I was bored. Again, it only lasts, a few months there. And then we gotta get rid of the stuff, okay? And so when we have to get rid of red blood cells, okay, that basically have this hemoglobin, which has iron, sort of dangerous, we're gonna produce bilirubin. How many people have heard bilirubin? Okay, now it's sort of interesting when it comes down to it, we'll talk about that a little bit later, that when you're a baby, or really a fetus, you have different hemoglobin than the mother and us, okay? Different conditions inside the body, right, for oxygen. And when you're born, you've got to get rid of that hemoglobin, okay? And actually then produce, normal adult hemoglobin. We'll talk about that. But we gotta get rid of all that. And so sometimes, basically, what might happen in a child? Jaundice. So this is a natural type of thing, right? You're getting rid of so many of the fetal red blood cells that you might have this idea of jaundice. Baby's happy. And supposedly, people tell me, somehow you put it under a blue light. Has anybody seen that or done it? What?
They have a belly ribbon blanket, or they tell you sunlight too.
Are they what?
Tell you to put them in the sun.
The sun itself. That's what they tell you. 21st century medicine. It gets better every day. Okay.
If you're
But it does somehow help, to metabolize this stuff down. So that's just cool. All right. So here we're about to get to the stuff that that we're going to concentrate on. Right now I'm not going to test any of those little things. Those are just like getting introduced. So anemias. Okay. Different types of anemias. Okay. You're not having functional hemoglobin. Guess what? We're going to do that today in lab. And look at anemias, okay, and sort of test for them. So I don't care too much about that. But this is something that we're going to concentrate on, something different. It's called polycythemia. And I am going to sort of use the board now and kind of get rid of that to talk about it. Because we all know anemias, and we'll do that here, but polycythemias are actually pretty important here for what we're doing in class. So let's get rid of this. I'm going to keep that guy up, of course. So, polycythemia. Polycythemia, right? It's really basically too high of a percentage of your blood of red blood cells. Kind of this idea of you will have a high hematocrit. Your amount of blood cells are, in comparison to everything else, is too much, and we'll kind of look at that. But here's where I want to use these slides and draw a couple arrows. There's two types, basically two types. There's something called relative polycythemia, which is basically the idea of dehydration. So if we kind of draw that though, so here's a normal hematocrit, kind of about 50%. If you look at relative polycythemia, we kind of do the same thing. Okay, we're going to have for this, I'm kind of draw it here, we'll do a little bit more. Okay, because this is dehydration. We'll have a normal amount of red blood cells. Of RBCs. But we have low plasma volume because we were dehydrated. So normal amount, but low plasma. So again, if you think about the hematocrit or percentage, again, this might be 5 centimeters, and I'll get out of the way for this, kind of like what that is. But let's say the whole thing then, if you're going to draw it out, is only 7 centimeters. We're really dehydrated, by the way, if it gets that low. And so then you could see your hematocrit is 5/7 times 100, and I don't know what that is, but really high, okay? So it is a high hematocrit, which is that idea, but it's caused by, again, the idea of you don't have too many red blood cells, all right? That isn't affected, but your plasma level is down, okay? And so that kind of comes to a couple things. Well, let's put the other one, and then we'll come back and look at it. The other way is, well, how do you think the other way would be? Here, you have the normal amount of red blood cells and low plasma. What would be the other way to have too high of a hematocrit?
Too many red blood cells.
Too many red blood cells. So we're going to draw that one. And so, again, we'll make, I don't have it right next to it, we'll make plasma level the same, 10 centimeters. But now we're gonna have this idea of we're gonna have a lot of red blood cells. We have high level red blood cells, so the red blood cell might be 7 centimeters out of a total of 10. So the idea, of course, that is still a high hematocrit. Okay, you can basically put that at 70%. Okay, so high hematocrit, but different thing. Okay, high level of red blood cells. What does that do to the viscosity? It's going to be really thick. We go back to that first day, we talked increasing viscosity is going to make it harder to flow. But what I like is this one. Okay, so well, two things. So what could cause too many red blood cells that we just talked about today?
The
EPO. Okay, that's where, again, if you are an athlete trying to cheat, trying to get that high aerobic capacity, produce more red blood cells with EPO, you could have a problem depending on what shape you're in. People have died, some athletes that try to do it. Because you're producing more oxygen carrying blood cells, but the blood is very viscous and really putting your heart under strain to pump it out. But again, how can this happen? And there are other diseases that can do this too. But you can think of at least high level of EPO could be one cause of this type of polycythemia, okay? Which again, just, it actually, it doesn't have a name up there, it just is polycythemia. But this one is a subclass of that, right? So all these are polycythemias, indicated by high number of red blood cell percentage, a high hematocrit. Two types. One is produced by too many red blood cells, by whatever reason, too many RBCs. Okay, one way to think of though is having high EPO. The other is representing dehydration, normal red blood cells, but low plasma because you're dehydrated. Okay, so here you're dehydrated. Okay, we're only going to concentrate on this right now. So you're dehydrated. Does that make you think of anything else? Blood pressure. What's going to happen to blood pressure
Too
if
high?
you're dehydrated?
Is it go up?
No.
Oh.
Okay, you want to think, and don't worry about this one, it gets confusing. You want to think of blood pressure this is how much fluid is in your blood. It is fluid that's pressure, right? I mean, I know blood cells might have some, but they, compared to the volume that it usually has on it, really the idea of that is if you are dehydrated, and this is kind of it, which means if you have relative polycythemia, that means that this is causing a decrease in blood pressure. This depends on the condition. We're not going to deal with that for blood pressure. So relative polycythemia, dehydration, kind of visualized by this. Loss of plasma volume, which is loss of basically blood volume. I should have kept that other thing up. And that means your blood pressure is dropping. And as soon as that happens, what do you think of?
Increase.
You turn to your back page. Okay? So another thing, basically, I can even put it up here that you can think of is dehydration. And again, also you might see relative polycythemia. Kind of round here, if you can write. Everyone see sort of the game, why that's so important here. I can be talking about multiple choice, which I do in the practice, about relative polycythemia, dehydration. I mean, part of that answer, I don't on that question, I might have, for relative polycythemia, all these might be, A or B or something like that. It's this, but I could say an increase in heart rate, or an increase in circulating sympathetic, or norepinephrine, right? Because that will be characteristic of this as well. Okay, that's why you look at the practice. I actually have at least one or two questions on that. You get the language of this. But anything I'm on this stuff, you can see if I'm relating to something causing low blood pressure. Part of the idea will be you will have a baroreceptor response. Okay, And that's why I'll have, and well, again, you're not writing all this out, but I could read that it's going to increase sympathetic, or increase circulating norepinephrine, or increase heart rate, okay? That would be consistent with this. The other polycythemia, I'm not going to put on blood pressure, because it actually depends. So that one I don't want to talk about, but this one is, dehydration. How about if, again, a former student came up and just came back out here and just cut me and I was bleeding, okay, bleeding out, okay? What would that do to my blood pressure? Lower. What would be happening? Beta receptor response. So blood loss. Okay. So the last thing, as far as new material, is I'm going to talk about platelets, but really idea of forming a platelet plug and blood clot. Okay, that finishes us off, except, I guess you could leave after that, it would be about 11, but you'd be not smart in a way, because I'm really going to talk about calcium channel blockers. It's kind of important for that one. So, but as far as just kind of new material here, again, platelets, you're not going to be memorizing this, but again, it is, comes from megakaryocytes, you have to know that. It lasts 10 days or so it doesn't last that long. But here's what I want you to know about it. And so this ending of this is kind of nice because it's actually not little factoids, it's a process. So again, as soon as that person cut me, okay, so you have an injury, we have a sort of a three-pronged step of controlling this. Hemostasis, right? Keeping the blood in the vessels versus coming out. And the first one is vasoconstriction. So again, these are local signals that will happen once something is cut to cause the areas around the injury to constrict. Okay, that's going to help limit. But here comes the ending here. The first thing that's going to happen after that will be these platelets. And we're going to show a picture. It's going to sort of block the hole, okay, the injury, and then later clotting will form. So here's where platelets come in. And again, just have that. So this is where their picture actually, even with this, is actually good to illustrate this point of how a platelet plug forms. So the first thing is, again, step 0, let's say before this, is normally the idea of these platelets are not sticky. And the blood vessels, I'm not going to test you on these particular items here. The blood vessels are releasing substances to make sure that these don't clot just in the blood, okay? But now we're going to have an injury, okay, upon damage. And so the idea is once injury happens, some of this exposed material here are going to signal the platelets to come to basically injury and now become very sticky, change their surface proteins. And so now they're going to start sticking together, okay? Here they weren't, boom. We're going to start to form again. You can see why they call it platelet plug. So you have this injury, signals these guys to come in, okay? And what the platelets do, and I'm not going to test you on the specific ones, not only do they start to stick to each other, they send signals out to attract other platelets, okay? So now those platelets are coming as well, like it says here, and then basically you have the plug. That's why this is very quick. Clotting is going to take a little bit longer, but we want to plug it up as fast as you can. It literally is those platelets. It really, that's why you look at these slides, but it really is this idea. Injury is releasing factors to attract the platelets, have them become sticky. Okay, you have these surface receptors, send signals out to get more platelets. Boom, platelet plug. Okay, blood clotting. Remember this? I've done that once. So what I want to say about this is kind of what I did before. I think I need to keep that up. Everybody good with this picture? Can I erase this part here? Ooh, I'm flying through this one. We'll see. All right. Usually I don't get the kidney stone until I guess I got 2.5 weeks when I'm teaching kidney. Then
Oh boy.
that would come and, we'll see. Yeah, I know. I want to time it right. Okay. So I want to erase this because again, all I want to write here is what I want you to know of this whole process. Again, it's very similar to I think I talked about at the beginning, but now it's at. So, again, just going back to this, and again, we're just going to concentrate on this. This is to remind us of, it's a cascade, okay? This is going to be a positive feedback, and the idea of this is, and we'll put this up here, we're starting off with all of these clotting factors that the liver produced. Again, liver, okay? Liver is making these different ones. A lot of them have these Roman numeral names, and then we have names that we kind of are familiar with. The liver produces these. And a couple of things that are important from that too. If you look at just the overall scheme of things, calcium seems to be pretty important. See, calcium knows it's the star. At the beginning it was like, what are you talking about, sodium and potassium, man, I'm it. You can see that. The other aspect though, that will become important, as you'll see in a couple slides, vitamin K is important as well. That actually is needed for synthesis of many of these. So the liver uses vitamin K to make a lot of these clotting factors. Okay, that would kind of be important. But the whole idea of this is, each one of those, it starts out as an inactive zymogen. Because we don't want to say, liver, we need you to make proteins. We want those there. So we don't want them active. So we're going to make, again, start off with zymogen, which is inactive. Okay, that's all I'm only going to have, yeah. So basically, a zymogen is inactive, okay? And again, it sort of has, it has the protein, but it has like an extra piece or something that makes it inactive. Then what has to happen is we have to take off that piece. So the idea is now we're going to, right here, you're going to use something which cuts protein, which is a protease. And then you're going to have the active enzyme. Because then, now our protein's able to fold, and you got rid of this thing that stopped it. So all these factors basically are like that. Except at the very beginning, you have these Roman numeral ones, and again, you see this idea of, it just gives Roman numeral 12, and then it becomes activated. And then it activates the next one, It's like a domino starting to fall, so we want the clotting action to happen. But as I said, I never even memorized all of those. I had to memorize everything back in the day. But these guys have names. So all I want us to know from this is, except I'll add something from one more slide on this, is those last two steps. Where you have, and I'm putting these, what's inactive and what's active. The inactive, and we'll start off with thrombin. Not what's before. Reactive is prothrombin. Don't worry about what protease works, it's the Roman numeral. It's going to be to the active form thrombin. So again, kind of the last two major steps of this. Then you have another, it's up at top, another zymogen, inactive, fibrinogen. So a lot of these have, pro-inactive or, basically something like that as a suffix, but I'm not giving you different ones. Idea is that thrombin itself is the protease for the next one, like the ones were above, they were Roman numerals. But prothrombin gets converted to the active form thrombin, thrombin converts the inactive fibrinogen to the active fibrin, which basically help form the clot. Okay, let's look at that, and then I have basically how we break up the clot, and then we're done. And then I would come back in 10 minutes. But so let's just make sure we have it. You're not memorizing the whole pathway. Vitamin K is very important, but the whole idea is we have something inactive that becomes active. So we have everything happening fast. We can light the fuse. The last two steps, all the guys at top are inactive. All the guys at bottom are active. We start off with prothrombin then, that's where we're starting out. it gets activated to the active form of thrombin. Thrombin, now that it's active, converts fibrinogen to fibrin, and we basically have our clot. Okay, once we have a clot, do we want there to stay forever? Answer is no. So pretty much the last slide will have what I want. The idea is we need to break up the clot, okay, as it's going. Now thrombin itself triggers something to break it up, and really this is where I want to put on this thing as far as breaking up the clot. Plasminogen. Plasminogen, also made by the liver, basically inactive, okay? Everything at top is inactive. That basically thrombin and, let's get rid of this thing, TPA, okay? Tissue plasminogen activator. How many people have heard of TPA? Maybe in the field, yeah. So tissue plasminogen activator, thrombin itself at a certain degree converts plasminogen to plasmin. Plasmin breaks up the clot, okay? So you have the system of formation of the clot, but you also have, again, plasminogen being converted to the active form. That doesn't come up very good. Basically, plasmin, okay, shown here, and basically TPA is the enzyme. I should put a little TPA, I guess. TPA converts plasminogen to plasmid, and again, plasmid is sort of the guy who helps break up the clot. So this is kind of a good last picture too, but I have something up there I want us to look at. So overall the process, everybody sort of get that. We have going over there, prothrombin to thrombin, thrombin converts fibrinogen to fibrin, but also, and really more on this, the idea when we have to slowly break up the clot, we're gonna have TPA basically convert plasminogen to plasmin, and then you'll start breaking up the clot. Now, TPA, of course, has anybody seen TPA actually used in a hospital setting, emergency setting? Well, what is TPA going to do? What if you have a clot that could cause a stroke or a heart attack? You want to break up the clot, okay? Maybe TPA would work. What if you have internal bleeding? Not so good. So then you sort of bleed out. So I think you have to sort of see, and again, that's where I need nurses to help, because I don't want some doctor who's doing something, okay? So I don't think you should do that, but I mean, that must be sort of a decision that has to be made on if they're forming a clot, there's also internal injuries, but that breaks up the clot. Okay, how about basically sort of drugs that break it up? Okay, and again, we'll actually look at different ones, like the heparin, etc. But really, the idea of these guys, okay, that when you look at basically Coumadin and warfarin, they are vitamin K antagonists. Okay, remember vitamin K was really important for production of these factors. Don't look at the other ones, even though they are important that you might get. Just the warfarin, Coumadin, vitamin K antagonists. That's the only question I would have on it. Yeah, like blood thinner, basically. Just decreases the production of those clotting factors. So you can see why that is more of a drug that could be taken, because you're not, TPA is just going to basically break up everything. That will just sort of decrease the number of clotting factors you have and decrease, that's why they call it a blood thinner, right, of circulating on that. But it does it by being a vitamin K antagonist. Everybody see that slide? That means that's the end of the material, except you really want to come back for at least some review, because you really need to see, I'm going to talk about calcium channel blockers and basically go and review. I'm going to put a picture up, sort of these four main things, looking at the two action potentials that we did first chapter, we're going to call it forcing contraction, and show you that's how calcium is involved in that smooth muscle. I'm going to draw four figures out, and a lot of them are going to relate to blood pressure. So kind of an important little concept that practice questions I hate you look at, but really I want to show that in class. So take 10 minutes. That probably is the last thing we'll do. I just want to make sure we do have that in class. And then lab, 12:20, we're gonna try to get some blood in you, okay, because we need some blood for this, and then won't be that bad of a lab, and we'll review for people for the test. So it'll take a few minutes. I'm gonna raise the board in a minute.